Hello again, everyone. So let us have a sample problem for USD. So given the following parameters of a rectangular beam, so the beam width would be 350 mm, the total depth would be 500, concrete cover 40, shear reinforcement 10, the concrete strength F prime C is equal to 20.7, and the rebar strength or the yield strength of rebar would now be equal to 420. So in this case, only one layer of 4 pieces 25 mm tension bars will be used. Okay, so these are the requirements. So the first requirement is the effective depth. So for the effective depth, that is once again measured from the furthest or the extreme compression fiber up until the centroid of our rebars. And as you can see here, only one layer of 4 pieces 25 mm tension bars will be used. So from that, guys, in order for us to solve for this particular dimension, we must first list the total depth. So in that case, our total depth here is now equal to 500 mm. But we have a concrete cover. So for our concrete cover, it is now 40 mm. So 40 mm. And the shear reinforcement here is 10 mm. So meaning that is this. So this is now our shear reinforcement. And from the shear reinforcement up until the centroid of the rebars is now equal to what do you call this, half of the 25 mm diameter bar. So once again, if I am now to, let's say, copy this to another slide so I can increase its size. So from this one here, guys, once again, this is 40 mm. Oops, sorry. So once again, this is 40 mm. And according to the problem, that the stirrup reinforcement is equal to 10 mm. And since our bar diameter is 25 mm, so from that, guys, half of 25 is 12.5. So once again, that is now equal to 25 over 2 or 12.5 mm. So with that being said, for the effective depth D, that is basically equal to the total depth 500 minus the concrete cover of 40 minus the shear reinforcement of 10 mm minus the half of our tension bar. So minus 25 over 2 mm. So from that, our effective depth is now equal to, so looking at the calculator to your left, so 500 minus 40 minus 10 minus 25 over 2. Okay, so our answer here is now equal to 437.5 millimeters. Okay, so this is now equal to, so depth is equal to 437.5 millimeters. Okay, so if I am to copy this to our next slide, and I will now be erasing this. What about for the steel ratio? So for the steel ratio, once again, rho is now equal to the total area of tension steel divided by the total area of the effective concrete. So from that, this is now equal to AS. So what is now the area of the steel? So since we have 4 pieces of 25 mm diameter rebars, so we will be multiplying this by 4. So 4 times the area of 1 rebar. So 4 times pi over 4 times 25 squared. So this is now in terms of millimeters squared. And for BWD, so for the breadth of the web or the beam width, this is now equal to 350 mm. So from that, that is 350 mm times, so is it 500? So incorrect, because this is the total depth and we need the effective depth here. So for the effective depth, that is measured from the top compression fiber up until, of course, the centroid of the steel rebars. And from that, we have solved for it as 437.5. So multiply this by 437.5 mm. Okay, so from that, the value of rho is now equal to, so looking at the calculator to your right, so 4 times pi over 4 times 25 quantity squared, or 25 squared, I should say, divided by 350 times 437.5. So our answer here is equal to 0.0128. Okay, so this is now equal to 0.0128. What is it? What is the unit here? So if the unit above is millimeter squared and the unit below is also millimeter squared, so when we see a ratio, it's actually unitless. So from that, our steel ratio rho is equal to 0.0128. Okay. So next up, what is now the balanced steel ratio? So if you can remember from our past video lecture, that is now rho balanced. So rho balanced is basically equal to, so if you can remember from our derivation before, but if you cannot remember, it is located here in this slide here. So you can either make use of, where was that? So you can make use of this one here or this one here. But since I do not want to solve for the strain any longer, I would rather make use of this formula. Okay? So if you want to learn more about how this was derived, just watch our previous video lecture on the derivation. Okay, so where was that again? So again, for rho balance, that is equal to 0.85 times F prime C divided by Fy times betas of 1 times 600 over 600 plus Fy. Okay, so confirming again, this was our derivation before. So 0.85 F prime C divided by Fy times beta 1 times 600 divided by 600 plus Fy. Okay, but what is the value for betas of 1? So for betas of 1, this is dependent upon what the value of F prime C is. So as a reminder that this is now our table for beta 1. So in this table here, so since our value of F prime C, so the F prime C in our problem is 21 megapascal, since it is less than 28, meaning that for our beta 1, we will be making use of 0.85. Okay, so from that, beta 1 is equal to 0.85. Okay, so for our raw balance, so raw balanced, this is now equal to, so 0.85 times F prime C of 20.7. Am I correct? So 20.7 divided by Fy of 420 times beta 1. So beta 1 is once again 0.85 times 600 over 600 plus Fy. Okay? So raw balance is now equal to, so looking at the calculator to your left, so this is now equal to 0.85 times 20.7 divided by 420 times 0.85 times the ratio of 600 divided by 600 plus Fy, and our Fy is 420. Okay? So from that, our answer here is, so let me just correct my computation here in the calculator. So our answer is 0.0209. Okay, so that is now our raw balanced. So again, for raw balanced, that is equal to 0.0209. Okay, so next up, let us solve for the, so for a moment, I will just copy this slide. Okay, so let me just erase my solution here. Okay, so next up, let us solve for the nominal strength. So for the nominal strength, once again, so suppose that if I am to draw the stress graph or the stress diagram here, so this is now our stress diagram. So this is now our compressive load. So this is now our compressive load here. So apologies, as this might take a while. Okay, anyway, so this here is 0.85 F prime C, and this here has a value of A. So this here has a value of once again A. Oops, sorry. Okay, so in the tension side, we have steel rebars there. So in here, for our steel rebars, this is now equal to AS times FS. Okay, so for the resultant of our compression block, I should say. So suppose that this is now the resultant of it. Once again, this is equal to 0.85 times F prime C times A B W. Okay, so for our moment, once again, so for letter D, for our moment M sub N, this is now equal to either get the moment about this point or this point. So once again, either you would be getting the moment about this point or this point, so it doesn't really matter. So once again, this is equal to 0.85 F prime C A B sub W times, so if this is now my reference point, what is now my lever arm? So our lever arm is this portion here. And if this is A, this is A over 2. And the total effective depth is D. So meaning that this is D minus A over 2. So from that, this is now D minus A over 2. Okay, so if you can solve for it using this equation, then just solve for it. And if we do not want to make use of this equation, we can also make use of the other equation as AS FS times D minus A over 2. Okay, so what is the value of Fs? If you can remember from our past video lecture, if the value of your steel ratio, rho, is less than your rho balance, it means if it is less than your rho balance, it means that the number of steel rebars is less than what is being required for the balance. So meaning, guys, that the steel members at the tension side would yield. So if it would yield, okay, so since rho actual is less than rho balance, as you can see here, so 0.0128 is indeed less than 0.0209. So from that, guys, we can now say tension bars yields. So from that, guys, it would yield. And if it would yield, we can now say that the value of our Fs is now equal to Fy. Okay? So from that, rewriting this equation, so updated, Mn is now equal to As Fy times D minus A over 2. Okay, so once again, you can either make use of this formula here or this formula here. Okay, so the next thing that we will be doing is for us to make use of either one. But take note here, guys, that in order for you to solve for this equation, we already know the value of F prime C, we already know the value of BW, but we do not know the value of A. So from that, we should solve for the value of A first. Even with this, guys, we already know the value of AS. We already know the value of Fy, but we do not know the value of A. So from that, let us solve for the value of A first. So if you are thinking if we can make use of A is equal to beta 1C, the issue here is that we do not even know the value of C. So with that being said, it would be better if we would be solving for A first using the summation of forces horizontal. So it's equal to 0, and from that, compression is equal to tension. So for the compression side, so looking at this diagram, for the compression side, that is 0.85 F prime C ABW. And for the tension side, that is ASFS. And since the value of rho is less than rho balance, it means that it will yield. And from that, Fs is equal to Fy. So from that, for my compression, this is equal to 0.85 F prime C A sub BW is A times B sub W, I should say. This is equal to tension, that is ASFS, but Fs is now equal to Fy since it would yield. And from that, AS times Fy. Okay, so substituting known values, this is 0.85. The value for FC prime is 20.7. The value of A is, well, actually A. Sorry, we are actually solving for that. The value for B sub W is 350. So this is now equal to AS. So our AS, once again, is 4 pieces of 25 bars. So this is now our AS. And for our FY, that is, I think, 420. So 420, okay? So 420. Okay, so from that, we can now solve for the value of A. So for the value of A, you can either make use of shift solve, or better yet, if you would be transposing them. So from that, this is now equal to, so 4 times pi over 4 times 25 squared times 420 divided by 0.85, 20.7, 350. Okay, so solving for the value of A, this is now equal to, so looking at the calculator to your left, so this is now pi. So 4 times pi over 4, the value of 4 would just simply cancel out. So pi times 25 squared times 420 divided by 0.85 times 20.7 times 350. Okay, so the value of A is now equal to 133.913 millimeters. Okay, so this is now the value of A. So since we already know the value of A, let us solve for it using any of these equations. Okay, so from that, Mn is now equal to, so if I would be making use of the first equation, this one here, so that is now equal to 0.85 F prime C AB W times the lever arm of D minus A over 2. So with that, this is now equal to 0.85 times F prime C of 20.7 times A. So this is now our newly acquired A. So 133.913 millimeters. Okay, so times, if that is now the value of A, times what is now the value of BW, I forgot. So that is 350. So 350 mm times D minus A over 2. So once again, the value of our D, or the effective depth, is 437.5. Minus A over 2. So the value of A is 133.913 divided by 2. Okay, so with that, the value of the nominal strength, or the nominal moment, is now equal to, so 0.85 times 20.7 times 133.913 times 350 times 437.5 minus 133.913 divided by 2. Okay, so your answer here would now be in terms of Newton millimeters. Okay, so from that, 305,576,008.9. Then again, your answer here is in terms of Newton millimeters. If you want to convert it into kilonewton meter, just simply multiply this by, or divide this by 1 million. So for every 1 kilonewton meter, we have 1 million Newton millimeters. Okay, so from that, dividing this by 1 million, so our answer here is 305.576 kilonewton meter. So this is basically our answer. So if we would be making use of the other formula, Mn is equal to ASFYD minus A over 2. So again, alternate. So Mn is now equal to, so ASFY times D minus A over 2. So substituting known values, this is now equal to, so pi over 4 times 25 squared times 420 times what is now the D, I forgot. The D is 47.5 minus A over 2, and our A once again is 133.913. So solving for the value of Mn. So pi over 4 times 25 squared. Oops, sorry. This should also be multiplied by 4. I forgot the value of 4. So 4 pieces of 25 rebars. So just multiply this by 4 by times 420 times 437.5 minus 133.913 divided by 2. Okay. So our answer here is 305 of 575,393 Newton millimeter. So as you can see that they differ a bit, but that is now dependent upon your rounding off number. So if you did not round any number, but actually we did here, but if for example that you did not round any numbers here, your answers must be exactly the same. But if you would be converting this into kilonewton meter by dividing this by 1 million, our mn is now the same. Almost. Okay. So which one of this will we use? So actually, let us make use of maybe this one here, since the value of a is only used once, and in here the value of a is used twice. But of course, it would be it is essentially the same. So it is up to you which one we will use. It is just that I want to make use of this value because I only made use of a once, and I know that when I have solved for a, I have rounded it to the nearest third degree or third decimal place. So again, for the value of mn, that is now equal to 305.575 kilonewton meter. So meaning that this is now its exact strength. So what about for design strength? So for the design strength, what does this mean? So for the design strength, this is basically equal to P times the value of Mn. Okay, so once again, it will be up to you which one of these methodologies you will be using. So where was that? So it is either you make use of this formula here, or look at this table here via phi and strain. But once again, I would prefer to make use of this graph, which is in terms of stress. So again, this is in terms of Fy, and this is in terms of 1000 megapascals. So if I am now to copy this, maybe here, if I am now to copy it here. Okay. So next up, guys, So I will now solve for the stress being suffered or being carried by the strain of my steel. So even though that we have used, guys, so take note here, even though that we have used Fs is equal to Fy here, we will not say that Fs is equal to Fy in terms of us getting the value of P. Because this stress here was based on the strain diagram, I should say. So this was the strain diagram. So what we did here was that we have just multiplied this by 200,000. And we also have just multiplied this by 200,000. And from that, if we would be multiplying them by 200,000, so just looking at this value, so 0.005 times 200,000, so that is now 1,000, and thus came this graph. So again, it would be up to you. If you want to solve for the strain, then do so. But once again, I want to solve for it via the stress. Okay, so for that, the value of Fs is equal to 600 times D minus C over C. Okay, so from that given, what is the value of C in our situation here? So actually, we do not know. However, we have solved for the value of A already. So since A is equal to, what was that again? So that is 133.913. And since A is equal to beta 1C, we can now say that C is equal to A over beta 1. Okay? So from that, C is now equal to what is now the value of A, that is 133.913. millimeters divided by beta 1, and beta 1 once again was 0.85, I should say. Okay, so from that, 133.913 divided by 0.85. Oops, sorry. So 133.913 divided by 0.85. Our answer here is now equal to 157.545. Okay, so that is now the value of C. Okay, so using this value of C, you can either solve for the strain. So for the strain of the steel, that is now equal to 0.003 times D minus C over C. If you want to make use of this formula, then meaning that your basis is this graph, okay? So if I want my basis to be this graph, instead of making use of this formula, I will be making use of this formula instead. So Fs is now equal to 600. So just multiply 0.003 by 200,000. So again, 0.003 times 200,000. That is now 600. So 600 times D minus C over C. Okay, so again, I will be making use of this diagram here. But if you do not want, just make use of this formula. Then compare it. So rest assured that if we did it correctly, our answer should exactly be the same. Okay, so from that, substituting known values, my value here is, or the value of C here is 157.545. So Fs is now equal to 600 times what is now D minus C. So D is equal to, so what was our D once again? So the D is 437.5 minus C, and the value of C is 157.545. So divided by C, which is 157.545. So from that, Fs is equal to, so this is now equal to 600 times the value of 437.5 minus 157.545 divided by 157.545. So our answer here is now equal to 1066.19 megapascal. So from that, guys, the value of Fs, or the stress that is being developed due to failure in our beam, is 1066.19, meaning, guys, that it is located here. So if this is 1000, since our value for Fs is 1066, meaning that if we would be projecting it upwards, our value is 0.9. So that is now the value of phi. So once again, for the value of PMN, that is now given by, so once again, PMN, this is now equal to, our phi is equal to 0.9. So with that, PMN is equal to 0.9 times MN, and our MN in our previous sub number is 305.575. So with that, this is now equal to, so 0.9 times 305.575. So this is now 275.0175 kilonewton meter. So this is now the design strength of the beam that we are analyzing. Okay, so if this is confusing to you, if you have solved for Fs equal to 1066.19, why is it the case that in our computation for the moment, we have used for Fs is equal to Fy? Okay, so once again, if you are asking yourself, or if you want to ask me, why is it the case that when we have solved for the value of Fs here, 1066.19, why is it the case that when we were solving for Mn, we used Fs is equal to Fy? Okay, so the thing is, guys, in our analysis, we cannot go beyond Fy, because if we would be reaching Fy, okay, so if we would be reaching Fy, it means that it would now yield. So it cannot go beyond Fy. So this answer here, so this Fs here, which is of course a lot greater than, so 1066.19. So this is of course a lot greater than 420. So this is just an indication that the steel really yields. So from that, since the steel really yields, and since it has underwent, or it has surpassed 1000 megapascal, so for our, where was the stress diagram once again? So since it has um, surpassed 1000 megapascal, it is now tension controlled, meaning that for our beam, the steel would yield by that much. Okay? But once again, when you are solving for the design strength or the nominal strength, do not make use of a value that is greater than Fs. So if your Fs is, sorry, do not make use of a number or a value that is greater than Fy. So meaning that if the Fs that you have solved for is 1066, which is greater than 420, use 420 in your analysis. But when you are solving for the value of the factor of safety, make use of this value. Okay? So also, if you do not want to make use of this, again, feel free to make use of this equation, which is 0.003 times d minus c over c. But this time, instead of you making use of this diagram, make use of the other diagram, which is this. So strain y, and this is 0.005. Okay? So there.